Hi everybody, my name's Chris Collison, and we're going to wrap up the summary today. And of course the goal here is really to identify what gaps you have in your knowledge before any final assessments. And in this particular video we're going to really look at chapters 6, 7 and the pieces that we pulled out of chapters 9, 10 and 11 of the Macquarie textbook. We have been doing some guided inquiry learning to help get through some of this material. So I'm going to try to give a description of how we've finished the course and the key points that are important as you make your way through towards the comprehensive final. So thanks for looking and good luck, and contact me if you have any questions. Thanks for listening. So we're going to start, of course, with Math Chapter E. Why do I bring this in where I haven't brought in any of the other math chapters? It's because of the importance of spherical coordinates. Okay, so we're going to convert those spherical coordinates. We're going to convert from Cartesian coordinates to spherical coordinates. So you've got to know how to do that. One of the important things is, of course, we've got the radius, or the radial distance, the distance from the nucleus. We also have the phi angle, which is the angle around the equator, and the theta angle, which is that north-south angle. So know how to convert from x, y, and z Cartesian coordinates into the spherical coordinates. We also need to recognize here the spherical coordinates volume element. And I'm just putting a nod to something that kind of comes up later in the course, how we need to work with del squared in the polar coordinates, in the spherical coordinates. It's a really complicated expression, but we need to do it because it makes the Schrodinger equation easier to work with. So it's a laborious conversion, and in this point I'm just saying we accept that conversion. So that's the Math Chapter E. So now we turn our attention to chapter 6, which was where the rigid rotator was introduced, and also the idea of rotational spectroscopy. We started at that point using this guided inquiry learning with the packets that I handed out, and that approach allowed us to familiarize ourselves, first of all, with the energy levels, and also the solutions to the Schrodinger equation that come in a lot later in the Macquarie textbook. And that approach is something that we saw later in the course, but it tells us where we're going, and it tells us that really we start to realize that the solutions are to the Schrodinger equation, those wave functions are written down in terms of theta and phi, and so we're going to have to do some work with that later. The textbook itself starts to introduce here the eigenvalues, so it provides the energy levels right off the bat. And we also recognize here, of course, in our classical treatment, so that's what we end up doing in order to build the Schrodinger equation. We have to build the Hamiltonian operator first, right? The radial distance is fixed. It's a rigid rotator. So we start to build that classical energy, and we do it in terms of angular momentum, right? So angular momentum comes in, everything is angular, everything is now involving these polar coordinates. We've got inertia now in there, which is a corollary to mass in the linear world, I suppose, and angular velocity. So that's again why we need these spherical coordinates to make headway. And then what we do is we use the approach from chapter 2 to separate the variables, so that we now have a theta equation and a phi equation, right? And so it turns out that phi equation can be solved really easily, and so we go on to do that, and we're all happy and dancing when we think about how easy the phi solution is. We later on go on to find how much more complicated the theta expression is. We'll come to that in a second. In the meantime, we start to look at rigid rotator spectroscopy. So this is brought in at different points. I plant certain seeds. We're told about this selection rule that delta J comes up because we know what the energy levels are. So we've been provided those fairly early on. So of course we know that in spectroscopy, we're absorbing a photon, and we're told there's a selection rule such that J must change, and the change is a plus or minus 1 in order for that photon to be absorbed by the material. We're also told here about the molecule. It must possess a permanent dipole moment. We continue some ideas there from chapter 5. If light is to be absorbed by a material, then we need that oscillating electric field to interact with something that oscillates. So a rotating permanent dipole is an oscillation that can connect and can resonate with an oscillating electric field that's applied to that system. We have these Q and R branches, so we talked about how there's these peaks and they look something like this. They're actually a lot finer than the way I've drawn them. And we've also talked about there being equal spacing between these peaks. And so this might be energy here in wave numbers on the x-axis. And there's this equal spacing. And so we have a Q branch, which is the low energy situation. And then there's the higher energy branch there, which is the R branch. So we've also got the rotational constant that's introduced. The whole idea of wave functions is brought in, and another way that we start to think about the spectroscopy. So this wasn't clear from earlier in the presentation. So we've got this piece in here, so the spacing in here is equal, and the energy is on the x-axis. As I said, we introduced the rotational constant. That's in wave numbers, and I also said that there was an important piece here about degeneracy. So as J increases, we're going to get a larger number of energy levels that for a particular larger number of states for a particular energy. So a larger number of eigenvalues and eigenfunctions for a particular energy. And so that degeneracy means that as we increase J, we start to see an increase in the number of energy states that could be populated, so that we start to as energy increases, J goes up. So at the same time, the Boltzmann distribution is an exponential decay. The Boltzmann distribution tells us about the populations of states as a function of their energy. And it turns out that the higher in energy that state is, the less likely it is to be populated, and there's an exponential drop-off. So that exponential drop-off looks something like this. And so when you kind of couple those two things together, you end up getting an overall shape that looks like the blue curve in here, and then we have these equally spaced lines. And that's what the rigid or the rotation spectroscopy looks like. And we can usually find it within the infrared spectral line shape within the spectral features of an infrared spectrum. So basically, the rotational energy changes are about 1,000 or 100 to 1,000 times lower than those for a vibrational transition, but we can often see them in a high resolution infrared or FTIR spectrometer. So that is what we talked about in terms of the spectroscopy of the rigid rotor. I think more emphasis was placed then on spherical harmonics, and so we jumped back into this theta function, which I said was really difficult to solve. And indeed, because it has constant coefficients, its solution, I said, was outside the scope of the class. That solution was based on Legendre's equation. So in the class, we developed Legendre's equation. We found out that the solution depends. So the eigenvalue solution and the eigenvalue solution depended on M and J. Later, we think about M and L for the H atom. So that Schrodinger equation solution depends on M and J. What else did we find out? We found out how the the magnitude of angular momentum squared commuted with the Hamiltonian operator, the difference being an inertia term, basically. They were very similar if you look at the two equations together. So we know that the wave functions must be the same for both. So that was an important stepping stone. We also, this should say, h bar is a fundamental measure of angular momentum, and then we later on went on to actually look at the orthonormal set of wave functions that were solutions to that Schrodinger equation for the rigid rotor. So again, these were the spherical harmonics. The spherical harmonics were the solutions to that Schrodinger equation for the rigid rotator, and those spherical harmonics would show up again as we looked at chapter 7 and the hydrogen atom, and as you can see, this is coming up next. So again, this is our summary, right? So then we started to look at chapter 7. This is really the main focus of the course, right? So in chapter 7, the eigenvalues, right, the energies for the Schrodinger equation were once again introduced. And what we ended up doing is we worked on these Pogel worksheets, chemical activity 7, 8, 9, and 10, and then later 14 and 15. So we start to work more with these Pogel worksheets to really get a feel for what's going on as we get to these really complicated solutions to the Schrodinger equation for these more complex systems. How are they more complex? Well, we'll take a look in a second. Remember those Pogel worksheets, they provided us with some familiarity to the solutions and the eigenvalues. As we transitioned from chapter 6, we started to think about angular momentum in the z direction and how that was quantized. That but angular momentum in the x or y direction is not quantized. There was a mathematical reason why we chose the z direction. The operator was a lot easier to work with. In chapter 6 as well, we also talked about the relationship between m and l, right? And so when l is equal to 1, m can take values from 0 up to and including plus or minus l, which would be plus or minus 1. So we started to think about m being the angular momentum quantum number for the z direction, right? So we then considered the energy of the hydrogen atom, and now the complexity comes into play because we've got the Coulombic attraction between the electron and the nucleus, and so the electron is tethered, but not in a rigid way. The electron can move around, right? And we start to think later about reduced mass of that electron because it's so small compared to the nucleus. We just consider the mass of the electron, really. And so we've got the Coulombic attraction between the electron and the nucleus, and we've also got the kinetic energy in here as well, always. So those two pieces, right, kinetic energy and the Coulombic interaction. Then, as usual, we substitute our operators in, and we develop a new Hamiltonian operator, and it's of course written in terms of the spherical coordinates. Del squared is in there in terms of spherical coordinates. We recognize that the radial distance now varies. The electron can really be anywhere at any distance away from the nucleus. We again use the separation of variables approach to arrive at that radial equation term. So we can separate the radial equation term from the spherical harmonics, and we could focus in that first part of chapter 7. We could think about the shapes of the orbitals, really just how they change as a function of distance of the electron from the nucleus. Turns out for the hydrogen atom, the energy of the atom only depends on the position of the electron in the radial direction. Okay, that changes for other atoms, as we'll later go on to see. Of course, we've got a radial kinetic energy, we have an angular kinetic energy, a potential energy. We separated all of those fairly early on. But for the radial equation, we worked on something called we didn't work on it. We have the Laguerre equations. Again, it was a differential equation that we would not solve. It could not be solved within the scope of our class. We would, of course, later look at the solutions. We plug them into the Schrodinger equation and verify that it all made sense. What are the radial functions? They are polynomials multiplied by exponentials. The polynomial just might be a constant, right? In the case of the s orbitals, right? We start with a constant. There is no factor of x in there. There is no x in there, and we just have a sort of exponential decay. As we go to other systems, like a p orbital, we start to see a linear increase initially, and then some exponential decrease. So we end up seeing something. Well, ultimately, we know what that looks like. We end up seeing a function that may have nodes in it, and it may also have negative values in it, depending on what that polynomial is. So the important thing here is there's some variation, there's some variability. There is this polynomial, it's always multiplied by an exponential, and so it'll always decay to zero in infinity. This was a particularly important part of this particular chapter. So you have to think about the shapes of those orbitals, and really the shapes of those orbitals do come from the Schrodinger's the Schrodinger equation solutions, right? An orbital is a wave function. Okay, so we have to think about those orbitals, and the shapes of those orbitals are associated with the wave function. So we looked in particular at the s orbitals and the p orbitals, and spent some time in the chapter working through those particular shapes. The next part of this chapter was, bridging our gap. We're starting to move towards electron spin, angular momentum, but we're also on the way. We're thinking about how we separate those, px, py, and pz orbitals when an external magnetic field is applied. So when m is non-zero, m is equal to 1 or 2 or minus 1 or minus 2, we get a splitting. So the energy of that system changes because of that angular momentum in the z direction. So the Zeeman effect is important for orbitals of quantized angular momentum there where m is greater than 0, and it also, we'd later find, it goes on to explain the Stern-Gerlach experiment for electrons that introduces the need for a spin quantum number. So we'll come to that shortly. What else is important in here? We get these wave functions. We're typically putting them in terms of their quantum numbers. So in here, psi is written psi sub 211. That's n is equal to 2. That's L is equal to 1, and that's M is equal to 1. And we might say, well, what is that? Is that an X, a P sub X orbital? Because we're familiar with P sub X from our general chemistry. We have to do a little bit more work. We have to get a linear combination of these spherical harmonics in effect to get the shapes of these P sub X and P sub Y orbitals in order to ensure that we don't have a complex number, actually. So this was interesting along the way. So check that out in your textbook. So the point here is that this P sub X orbital is not exactly the same as the wave function psi 211. That, remember, the psi 211 is a solution to the Schrodinger equation, and this kind of, I guess, the py orbital or the px orbital, these are linear combinations as described in here. So try it, plug in those equations and see what you get as part of your review. We later kind of all got confused by electron spin. Spin is really unusual. I think There are some parallels with spin orbit or angular momentum, but spin is basically something in and of itself, and so there's going to be some problems here. But we have spin operators now defined as s hat squared and sz hat, and these come about because of their analogy. They are analogous to L squared and L sub z squared. So that's really the connection there. So they are considered as a form of spin angular momentum, if you will, for the electron. So we can also think about certain eigenvalue equations for spin in particular that are somewhat different to the Schrodinger equation. So they're a slightly different entity, separate entity. And the capital S here is the magnitude of the spin angular momentum, and little s here is the spin quantum number. And really, these are chosen because they're analogous to to capital capital L and L for the orbital angular momentum magnitudes that we think about for an individual electron in an atom, or the orbital angular momentum. Okay, so moving on, and again, I remind you, if there's gaps here in your knowledge, if some of this doesn't make sense, go check it out in the textbook, make a note of something that you want to take a look at. We started then to think about approximation methods and many electron atoms. We again referred a lot to the guided inquiry learning packets. And the point here right off the bat was that the Schrodinger equation can't be solved analytically for more complicated systems than the hydrogen atom. So basically, the more we start adding one electron, we have a repulsion of that electron in the hydrogen atom, and we now cannot do a paper and pencil calculation of the Schrodinger equation. We have to use a slightly different approach. So there's a couple of approximation methods we use. In the guided inquiry learning example, we used helium as an example. We used trial rate wave functions here that involved the products of, for helium, it was an 1s orbital multiplied by another 1s orbital, and the Hamiltonian now is developed to address each electron separately. It's separable, and therefore we end up getting we end up starting to use something called the variational method, or the variational theorem, and it turns out that we find an approximated trial wave function, improved trial wave function. What could we change in that trial wave function? We ended up changing capital Z, which was really effectively the effective nuclear charge. So in this variational method, you can find an energy minimum because we know we're not going to go any lower than the true energy of the system. So we always calculate using quantum mechanics an energy that's higher than or equal to the true energy. So we know we're never going to go below. So by finding the energy minimum using calculus, we can vary the coefficients, we can vary the effective nuclear charge in the trial wave function, and we can come up with a better description of the system. Remember, the wave function is a complete description of the system. We also looked at perturbation theory in one of the classes, and we went through that. We didn't linger on perturbation theory a lot. It would be more important for a more advanced class in quantum mechanics. And then lastly, this is very recent to us in time perhaps, but we looked at Pogel exercises that introduced the Huckel molecular orbital theory for conjugated molecules, and this was interesting to us because we could see that the electrons, we know from benzene rings, for example, that the electrons are smeared out over, in that case, 6 particular atoms. And we looked at some exercises involving imidazole, and we looked at butadiene, and we basically recognized that those single electron orbitals would actually be spread out over multiple atoms. And that was one of the key ideas from that Huckel molecular orbital theory. Works well with spectroscopy and with pi bonded systems. I used that as an illustration to link us to linear combination of atomic orbitals, and I described how for a hydrogen molecule, for example, we can sum together, with a constructive interference of two 1s orbitals, one on each of the atoms. You can build a molecular orbital. A bonding molecular orbital would involve this additive constructive interference of the wave function, wave functions on both of the atoms independently. Subtractive, they should say, subtractive or destructive interference of the wave function leads to something called antibonding orbitals. So constructive interference leads to sort of more energy or more electron density between the two hydrogen atoms, sort of in this region here. That was a constructive additive molecular orbital. And we can also see something where when we have a subtractive combination of these atomic orbitals, we end up getting a node of electron density in between the two atoms, and therefore there's less electron density in there compared with the individual atoms, and so those nuclei repel each other, and so we end up having a higher energy situation if we put an electron into that molecular orbital. As I said, that illustration of the Huckel molecular orbital, pi orbitals work that we did in chemical activities 14 and 15 is also representative of the sigma bonding orbitals in the hydrogen molecules. I also just said that hybridized orbitals, what we're doing there is we can consider one electron in a combination of orbitals. So we might take a 2s orbital and a 2p orbital, and we kind of sum them together actually, and take a little bit of say coefficient, a little bit of the 2s orbital plus a little bit of the 2p orbital. We sum them together, we're going to get some linear combination of those orbitals. This is an approach where we take a linear combination, and it turns out that combination can be used in our trial wave function, and it ends up giving us a very visually appealing approach to bonding, and we can start to understand the geometry of molecules. This will kind of take you back to general chemistry, so we didn't really linger on this for too long, but this is it's a linear combination here of the different orbitals that leads to hybridization. And we stopped at that point and said that's molecular orbital theory. We can take the Schrodinger equation for the hydrogen atom, we can expand that to include multiple electrons, we can expand it to have multiple atoms. If you would then take my molecular photophysics class, which is really a second course in molecular spectroscopy, then we'd start to think about how time is important for those transitions. We start to think really about connecting electrons from one orbital to a higher orbital. How does that actually happen? But we are limited to the scope that we cover in this course. So that is the summary. Again, if there are gaps in your knowledge, please, this particular video is not set up to tell you everything. It's basically a review. So if I say something and it makes no sense to you, go and look it up in the textbook. So thank you very much, everyone, for listening. It's good to see you all, and you've now reached the end of the course, and good luck on whatever you choose to do next.